Hello, everyone. Welcome to our next portion of Lecture 1. We're on Lecture 1G, where we're going to look at changes of state and focusing on how gas properties come into play with our changes of state. So at times in the past, we've definitely stressed the relationship between molecular structure and properties of those molecules. So structure and properties becomes a very important relationship between molecules. Both physical and chemical properties are affected by the structure of a molecule. So here's just a very simple example of two molecules that have the exact same chemical formula, C2H6O. So we have ethanol and dimethyl ether. You can see that they have a different structure where you've got the ethanol with the OH on the end. The dimethyl ether has the oxygen in the center of the molecule. And if we look at the boiling point, we can see that the ethanol has a boiling point that is nearly 100 degrees Celsius higher than dimethyl ether. And that's a very significant difference for two molecules that have the exact same chemical formula. Now, the primary reason for that is we see on that ethanol molecule there, it does have an OH sitting on the end of it right here, and that can lead us to hydrogen bonding, whereas the oxygen in the dimethyl ether is just attached to two carbons, and so it will create a slight polar situation similar to acetone, but not quite the same. And so it does have a very low boiling point, well below room temperature. So we can take a look at the three states of water. We'll be talking about different states of water. This shouldn't be news to anyone here. If we look at gas, liquid, and solid, we see that water turns to a gas at boiling point at 100 degrees Celsius. Has a very low density, as you might expect, because it is a gas. Just as a molecular view, you can see the molecules are spaced very far apart. They don't interact with each other. As a liquid, so just as an example, somewhere between 0 and 100, so the author here chose 20. Density, roughly 1. We generally approximate that at 1, but it can vary just a little bit. Has a molar volume of about 18 milliliters, so we usually think of 18 with a density of 1, you're going to get 18 grams per mole, and you're then going to have a molar volume of 18 milliliters per mole as well. And so you can see that the water molecules aren't particularly arranged in any order. They're kind of chaotic. They do move around. They are touching each other, but it's kind of like being at a dance where everybody's dancing with everybody else. And then you have our solid, which starts at 0 degrees Celsius and goes below. Has a lower density, which allows ice to float. Has a molar volume of about 19.6 milliliters, so its molar volume is a little bit higher, which is indicative of the lower density there. And in the molecular view, you can see that the water molecules are arranged in very specific ways. They have a very different orientation, which is very common for crystalline solids. If we look at some of the properties of these different phases, gases tend to have a low density. We see that with water. An indefinite shape, a gas will always fill the container that it's contained in. That's why its volume is indefinite. It's whatever the volume of the container is, that's how much gas you have. The strength of the intermolecular forces relative to the thermal energy is always very weak in a gas. It's why it's in a gas phase. Now, in a liquid state, the density, I wouldn't have said high, I would have said medium. Its shape is indefinite. A liquid will take the shape of whatever container it happens to be in. If you put it in a cube, it's going to be a cubic volume. If you put it in a cylinder, it's going to be a cylinder volume. If you put it in a star, it's going to have a star volume. However, you can't change what the volume is. If you have 5 milliliters of water, it doesn't matter what container you put it in, you're going to have 5 milliliters of water. If you put it in a 15 milliliter container, you still only have 5 milliliters of water. Very different from what you have in a gas. The strength of the intermolecular forces relative to thermal energy, again, is moderate, which is why it's in a liquid state. You do have some molecules that can go into a gas phase, as we discussed in the previous lecture, but most of those molecules are going to remain in the liquid state. And then you get to a solid, fairly high density, has a definite shape. So whatever shape the solid is in, you can put it in any kind of container. The shape of the solid is going to remain whatever shape it was. And the volume is also definite. Again, you put it in a container, it doesn't change what the volume of the solid is. And the strength of the intermolecular forces relative to the thermal energy is going to be very strong. In other words, the thermal energy has dropped so far that the intermolecular forces cannot be overcome, and so much stronger than what you have in the thermal energy. So let's look at a change of state. So we can change the state of matter in a couple of different ways. We can change the pressure or we can change the temperature. So if we look here at what we have for moving from solid to liquid, now the change from solid to liquid pretty much only happens with a change of thermal energy. So if you have a solid, you want to turn it into a liquid, you've got to add heat. If you have a liquid, you want to turn it into solid, you have to remove that heat, so cool it down. Now, if you want to go from a liquid to a gas or vice versa, you can do it in a couple of different ways. To turn a liquid into a gas, you can add heat, which adds thermal energy, or you can reduce the pressure, which is in essence increases the vapor pressure of that liquid and causes it to turn into a gas. Now, if you want to go from a gas into a liquid, you can cool it down. That lowers the thermal energy, or you increase the pressure, thus increasing the amount of space or decreasing the amount of space between particles by decreasing the volume perhaps, and they start sticking together and become a liquid. Or you can do a combination of those two things as well. So this seems like kind of a strange switch looking at air conditioners, but it is a very good study in phase transitions. And it gives us a very common point of reference because we're all familiar with air conditioners. So how do they work? Well, one of the ways that they work, or one of the things that they do, is they remove humidity by cooling the air. And so remember, humidity is just nothing more than water vapor in the air. And one of the things that they want to do initially is to remove that humidity. And the reason they want to do that is because water takes a lot of energy to change the temperature of. And so it's easier and more energy efficient to cool the air by not having water in the air. So it removes humidity. So you cool the air, water condenses out, and it makes your air feel drier. Now, let's think about that, however, because in our air, we have other gases present. Obviously, not just water. We have oxygen, we have nitrogen, we have some argon, we've got a little bit of helium, there might be a little hydrogen, maybe some methane floating around, who knows? There's a lot of different gases in our everyday air. They're getting passed through the air conditioner at the exact same time as the water. Now, the water condenses into a liquid, but those other gases don't. They're cooled down to the exact same temperature, but they don't condense as liquids. Question we want to kind of stick in our mind for a little bit is why. So let's just think about what's happening inside of our gas that's passing through an air conditioner. So you've got atoms and molecules moving very rapidly due to thermal energy. At room temperature, molecules are moving, give or take, 1,800 kilometers per hour. That's pretty dang fast. Now, if we cool a gas down, we remove thermal energy, that's going to remove kinetic energy, and so the atoms or molecules begin to move a little bit more slowly. So less heat, less energy, lower speed. So can we say that the water becomes a liquid simply because the molecules were slowed down? Well, we can a little bit. We can say that for the water, however, it still does not explain what's happening with the other molecules. Because the other molecules in the air were cooled down to the exact same temperature, but they didn't condense as a liquid. So there has to be another factor other than just the temperature. Well, let's go back to what we know about a water molecule. We know that water molecules are polar. The oxygen is highly electronegative, and so it pulls in electron density from those hydrogen-oxygen bonds right there, and it creates a delta minus on those oxygen atoms. Now, also because that electron density is getting pulled away from the hydrogen, it creates a delta plus on the hydrogens of all of the water molecules. And so you have partial minuses. Remember that delta means a partial. So you have a partial minus and a partial plus. Well, even though they're partials, they're still positives and negatives. And of course, we know that positives and negatives attract each other. So Generally, when water molecules are passing each other in the gas phase, they're moving too fast in order to stick together. However, once you lower that speed enough, they can begin to stick together. It's kind of like moving magnets back and forth. If you move two magnets in your hands past each other very quickly, they won't stick together. But if you move them past each other very slowly, they will probably stick together. So in the gas phase, the attraction is too low to overcome the kinetic energy. However, as you cool that gas down, the speed of the molecules decreases, the kinetic energy decreases, and if that gas gets cooled down far enough, the attractive forces can overcome that kinetic energy, and the molecules begin to stick together, and this is what we call condensation. Okay, so the temperature where this begins to happen is the boiling point. Okay, or, well, the boiling point is really kind of where they start coming apart. Going the other direction from gas to liquid is the condensation point. It's the exact same point. It's the exact same temperature. It's just a matter of what direction you're coming from. So now we know why the water gas is turning into a liquid. We're cooling down the water vapor in the air. It's slowing down. We know that water has a strong dipole, has hydrogen bonding, and so those water molecules begin to stick together and condense out. But it still doesn't explain why gases like nitrogen N2 and oxygen O2 don't turn into liquids at a similar temperature. Now, we could just say, well, H2O is polar, N2 and O2 are nonpolar, so they must not have any intermolecular forces. But we know that that's not going to be true. And the reason that we know that that's not true is because we know that oxygen, nitrogen, and carbon dioxide, CO2, all exist as condensed phases, just at very low temperatures. Oxygen exists as liquid oxygen. It's a very common rocket fuel. Liquid nitrogen is used lots of times. We have a big tank of it sitting in our labs to help cool the NMR machines. And carbon dioxide goes from a gas phase directly into solid phase under normal atmospheric pressure. And that's what causes that's what is dry ice, solid CO2. So we know they all exist as condensed phases, just at low temperatures. Well, how low are those temperatures? Well, they're really low. They're cold. Dry ice forms at minus 78 Celsius. Liquid oxygen goes down to minus 183, and liquid nitrogen has to get cooled down to minus 196. So very cold. So we know that these molecules stick together, but we know that they are nonpolar. So what is causing nonpolar molecules to stick together? We mentioned that water is a polar molecule held together by its delta plus, delta minus ends. We also know that nonpolar molecules form condensed phases, however, at much lower temperatures. So there must be an intermolecular force that is involved to help those nonpolar molecules stick together, but it's going to be much, much weaker than the dipole of something like water. So I'm going to leave you with that mystery for now, and we will take a look at that much more closely in our next lecture.